Greg Nault. He's going to talk to us about UHPC overlay solutions that Zach mentioned earlier. Greg is an engineering project manager with Lafarge Holcim, a multinational concrete material supplier that manufactures ultra-high performance concrete.
I'm going to build on what Zach kind of started talking about here as far as UHPC goes. But basically, it's a concrete material. Cement, sand, silica fume. No coarse aggregate in this technology. It's all very fine particulate. You add a fairly low amount of water to cement ratio, generally less than 0.3. A heavy amount of superplasticizer to keep it flowable. And then once it hardens and you cut it, a heavy dose of fibers as well. And you can see all the nice shiny flecks in the material. So these are all these tiny microfibers that Zach had talked about earlier that are really fairly well evenly distributed throughout the cross section. And those play a pivotal role as far as crack control and tension strength is concerned. We already saw the material flow, but just to give you another visual representation of it. We have kind of two versions. One we call a self-leveling version. It basically flows where gravity wants it to flow. But what you can see is there's a little bit of a stickiness to this product. And that's generally due to how fine all the particles are. There's just a lot of kind of cling to each other. But it does flow where gravity tells it to go. It will leak through any tiny void or hole or crack that might exist. So forming becomes key in various applications. On the other side, we have a thixotropic version. So this is what we're going to use for overlays because bridges have slopes. And if we use a self-leveling product, it's going to go where gravity tells it to go. So we use a different admixture that kind of gives it a little bit of a thickening behavior. But really, as you're imparting energy into it, the material looks like it's fluid. And then as soon as you take away that energy, it kind of stiffens up and maintains that form that it's in. General properties, we kind of already touched on this, but everyone talks about compressive strength. But again, to Zach's point, I think that's really not the driving factor here. We're really looking at the impermeability and the durability of this technology here. So just to give you kind of a visual example, the top two lines are what would be kind of a more conventional high-performance concrete mix. And this is a test that measures the amount of current that can pass through a specimen. You can see a UHPC mixture versus a high-performance concrete mixture. Much, much lower current passing through, which is a representation of how permeable or impermeable the material is. And then, of course, we also look at cracked properties. The photo on the bottom left there is basically a section that has been cracked intentionally, and you can kind of see the fine micro cracking nature of this material, really all held together by these fibers. Impermeability is just one kind of parameter. We have good abrasion resistance, we have good freeze-thaw resistance. I mean, you name it, in comparison to high performance or conventional concretes, we're much lower than these other mixed designs. And this just gives you kind of a side-by-side comparison of what these might look like. In Europe, they've kind of developed this technology a bit further than where we have in the US right now. And if I look at the French standard that has really adopted this technology, if you can read this, basically we're looking at the minimum amount of cover clearance that you need to put over a black rebar to satisfy a certain design lifespan. And the table on the right there is basically showing you three lifespans, 50 years, 100 years, 150 years, under various exposure conditions, with XF4 being an environment that has heavy freeze-thaw and salting effects. And basically the table on the left is telling you what your cover needs to be. And the bottom right box there that's circled is kind of your worst case condition. And what you see is 25 millimeters of cover. So what has been shown through various testing is if I put 1 inch of cover over a black rebar with this technology, then, and using what we'd consider a standard UHPC, I can guarantee 50 years of service life before I start to see any corrosion of that steel. Now, if I used what we call enhanced UHPC, something with a little even better durability, we can get up to 100 and 150 years without increasing cover. Now, of course, you could increase cover and basically get longevity as well, but you can also do it by tweaking the mix design itself. The tension behavior is really unique to this stuff. These fibers in there, they really create a multi-cracking behavior, and all these cracks are kept to a very fine micro size. So they virtually remain impregnable to chlorides and water and acids and aggressors and all these fun things that deteriorate our structures. But they also add a neat feature is they give concrete flexibility. So you can cast a very thin panel of this material and you can literally bend it like you would a plywood piece. So obviously you're not going to do this to your bridge deck, but it shows you in order for this element to bend, hundreds of cracks have to be forming to give it that displacement. And you can't really see one singular crack anywhere on this element. So all these cracks are very fine and evenly distributed across the stressed area there. So where this comes into play is when we look at bridge decks. You know, everyone here understands that they deteriorate quite quickly and they need repair and rehabilitation and preservation. And so UHPC overlay is one way to do it. If you let your bridge deck go too far, you end up having to replace the deck itself. And what you might have heard with UHPC before are precast connections. And that's kind of where this technology got its start here in the US, is looking at full bridge deck replacements, putting in precast panels, and then gluing everything together with UHPC. And there's literature you can refer to by FHWA that goes into more detail on that. And you might end up with a new bridge deck that looks something like this, where you can clearly see the dark lines where the UHPC was poured. Up in the Northeast, we've done a ton of these projects. You can see all the dots ranging back from 2005 up until the end of 2018, and of course there's more dots that'll be put in here this year. But the idea here is really to get onto the bridge deck before it's gotten to the point where it needs to be fully replaced. So can we kind of do a partial depth removal and rebuild that back with UHPC rather than having to replace the deck in its entirety? And so there's kind of three concepts that have emerged over the years. Ideally is really number one. We get on the deck early enough when the contamination hasn't gotten too far gone, and we only have to remove a marginal amount of cover, maybe an inch, maybe an inch and a half, and then we can build that back with this very durable, impermeable material. But if your concrete has gone too far, your rebar has already started to corrode, you have delamination kind of down at the rebar level, you'll likely have to remove past that point. Generally, we'd like to get about 3/4 of an inch underneath the top mat so that the material with these fibers can really get around all this rebar and surround it and encapsulate it. In the last instance, number 3, you might be looking to strengthen your section as well. So not just rebuilding back a layer, but adding some strength to it. And in that case, you can build on top and put in supplemental reinforcing steel to give you additional tension capacity where you might need it. As of 2016, we've completed 8 bridges using ductile UHPC technologies. These are 5 of the bridges, and you only see 4 photos because the last bridge in Delaware actually was 2 bridges in parallel that were done. But we started in Iowa in 2016. We did a project the next year in Delaware, then we jumped back to Iowa in 2018, and then we jumped back to Delaware in 2019. And you can see some of the stats here on these. They weren't very large projects, anywhere from 1 to 3 span bridges really. And really a lot of these are using concept number 1. We're not really exposing that top layer of steel, we're just removing down kind of the cover and then building back 1.5 to 2 inches or so. Earlier this year, we did a 3-bridge package in New York State, down in the Hortonville area. Kind of a unique structure where they had these adjacent voided slabs, and they had seen some reflective cracking or the piano key effect, as we heard before. Their idea was, well, let's try to restitch everything together with a UHPC layer. So they went back and did about 1.5 inch strengthening layer on top of that system. So this was the bridge in Iowa back in 2016, 1.5 inch removal and replacement. And generally surface prep, exactly like the last presenter talked about, you can do this on a milled surface, you can do this on a hydro demoed surface. The hydro demoed surface tends to be preferable in the sense that it's going to bust away whatever poor concrete is there. With a milling effect, you might not get everything, and actually we saw this on the Iowa job. They did a mill, which is shown on the left photo. They poured the overlay, and then after everything was done, they went back and did a chain drag, and then they found that there actually was some delamination. It wasn't between the UHPC and the substrate, it was underneath the rebar where the poor concrete had not been fully removed. So if you go more the hydro demo route, you're really going to get that material down to sound substrate material. As far as mixing equipment goes, it really depends on the size of your project. Right now, we've been doing fairly smaller bridge projects, so the mixers on the left-hand side are what we've been using. They're basically transportable pan mixers or horizontal shaft mixers that get set up on the job site, and they get loaded with all the materials right there, batched on site, and then transported to the bridge. But as your project size grows, you might have need for a ready-mix truck or even an on-site batching plant of sorts. And then placing equipment, we use fairly regular equipment. The top left there is just a vibratory screed, steel screed, that was used on a couple of these projects. The bottom left is basically the same thing, a vibratory screed, but a little more refined. The contractor on this job had it on a rail-mounted system to kind of give them more ease of movement with the system. And on the right there is a large placement machine that's kind of been specially designed for placing UHPC, kind of originated in Europe. It's more used for larger placements where it would justify something of that size. So this is the first job. You can see the finish on this was not great. The contractor that did this, we kind of rushed through this job, unfortunately, and they used a screed that had a very low vibration input. And so the screed wasn't really consolidating the material as it passed over. It was kind of dragging the material, and we ended up with a very, very rough finish. What we've seen on subsequent jobs is if you have a screed with enough vibration, you get a pretty clean, kind of stricken surface. But nevertheless, on a lot of these jobs, they come through and they do a post milling process anyways, using a milling machine, which either you're using before to prep the deck or after to kind of finish off the deck. And this is a couple photos showing that milling process here. Generally, we take off about 1/4 of an inch, and you can see on the right-hand side kind of that finished milled surface look in the fresh state there. And then some agencies, they'll also groove the deck. I've seen it in some agencies, some don't. Use the same equipment that you would use on conventional concrete to come through and do a grooving on this material. Kind of a shot of that Iowa project back in 2016. The left-hand side had been milled and the right-hand side had been grooved, and they're continuing to groove on the left-hand side with the machine there. And this is what the riding surface looked like about a year later after the job had been done. So you'll see kind of an orangish hue to the deck. So during that milling process, you do expose a little bit of those steel fibers, and whatever has been exposed will kind of corrode off the surface. But on the right-hand side, you can see that the fibers any fibers that were sticking up have disappeared. They've just kind of left behind a nice historic-looking corroded surface there. So another job in Delaware, this was the second one, a little bit of a different situation. We had an adjacent box beam system, actually a new superstructure where they were using UHPC both in the joints to connect the boxes together and then as an overlay to kind of give an impregnable seal to the box system. And they also used it at the ends of the beams to cap everything. So a couple photos from this, you can see the box beams there and them filling up the ends of the beams with our self-leveling version. And then we did a pre-construction mock-up with the contractor on this, which we highly recommend if the contractor has never done a UHPC overlay work before, because it does behave a little bit differently than what they're likely used to. And here's a little video of that mock-up showing. So you can see it kind of flows out fairly fluidly, and then the second it starts to spread, it really kind of stabilizes on itself. And then we just have guys with some rakes, shovels, moving the material around in front of that screed. Pretty easy to do, quite frankly, but you need to have enough folks to be out there to do it properly. They had a roughened surface to pour against. They pre-wetted that surface before they placed the material. And on this job, since it was a small enough project, we provided materials in bagged form. So on the left, you see the pre-bagged premix. And then on the right are bags of steel fibers and tubs of superplasticizing admixture. And we had these smaller pan mixers. Each one can mix about 2/3 of a yard per batch, and we have 2 of them working in tandem. We can do about 3 batches per hour. to give us an output capacity of about 4 cubic yards per hour there. And there's a guy loading the bag in the mixer here, and then another video of them placing it on the bridge deck itself. So again, spread it out with some rakes in front of the screed, and then we hit it with a heavy dose of curing compound after the screed has passed over. The screed has high energy input to really consolidate the material as it passes over it, and then we cover it with plastic for curing. We don't have to wet cure it. We just want to seal in the moisture that is already in the mix itself, and let it cure for about 2 to 3 days. And so this is the strength curve of this material. We've generally been targeting about 10 KSI before opening to traffic. And depending on your temperature out there, you're going to get that in about 2 to 3 days with this particular mix design. We're working on improving that to hopefully get that in a day or so, and that's ongoing. So this was a well-attended job site by Delaware DOT. I think they had everyone from their bridge office out there to watch it, which is good, helps disseminate the information quickly through the team. And then after they milled it, this is kind of the final riding surface here. So a couple other photos just to show off the other projects. This was another Iowa job in 2018, a little bit larger production done by Wallow, and kind of the final surface there. And then another job earlier this year in February. So we had some heating elements as part of this due to the weather conditions out there, but this was the 2 parallel bridge that was done by UHPC Solutions here. And then one more video here showing the placement. So this was a little bit of a bigger job, so we had a front end loader that we kind of used instead of those motorized buggies. And we could come out and dump the material right on the bridge deck in front of the screed. A few shots from the New York job from earlier this year. They did a hydro on the deck and then placed the material, and the white is the curing compound they put on afterwards. I'd be remiss if I didn't mention Switzerland in here. The Swiss have really done a lot of this technology. They've done over 70 bridges now to date, and most notably has been the CHILLON viaduct. So this is a kind of a signature bridge where they strengthen this entire system using a UHPC overlay about 2 to 2.5 inch thick. And this is the cross section of that box section here. And there are guides published by the Swiss that will show you how to strengthen, how to design for this type of a situation. I'm not really going into that, but it can be used to that effect if needed. And because of the larger scale of this job, they had an on-site batch plant. They used their specialized machine for this placement, which made things go quite quickly. I think they did this entire bridge in about 30 days, 2 twinning bridges. Quite a few coming up still. Delaware has a 3-bridge package that's coming up. New Mexico, I know, is trying to do one. New Jersey has a 5-bridge package they're looking at. New York has 3 or so bridges in their pipeline. And then the Commodore Barry Bridge is looking at doing a demonstration pour next year, kind of isolated sections to try this out, and other projects as well that we are actively tracking. If you want to learn more, the FHWA has published some guides on this. You can refer to those. Iowa State University has done quite a bit of testing on this, looking at the bond strength and everything, and all looks pretty good. So just to close here, talking UHPC overlay, and Zach had shown some other ideas. Joint headers, link slabs, connections, beam encasements. We did a joint header up in Colorado last year in an area which uses a lot of heavy truck traffic in the winter with chains, and it's held up very well so far. We've done a ton of link slabs in the New York State area, and now Delaware is starting to do some, as well as West Virginia, Maryland. So if you want to eliminate the joint completely, you can put in this flexible linking element to remove that. And then as Zach talked about, beam encasements, which is really kind of a brainchild of University of Connecticut that is coming to fruition now to encapsulate these steel girders. And jacketing as well. So if you have piers that need some TLC, you can remove the deteriorated concrete and put a thin jacket of UHPC around there. So if you want to learn more, go to our website, www.ductile.com, or our Vimeo page, and you can see some more videos like we showed here. Any questions?
Well done.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.